Hello everyone, welcome to this RECode 3.0 event conducted by the Coding Club of BSc College of Technology. I am Dhanushkumar from 3rd year BSc G2. In this video, we are going to solve two interesting DSA problems step by step. We will cover the following aspects for each problem: problem description, sample input and output, and then we will break down the approach and algorithm, followed by the optimal source code and execution of the code with sample inputs and outputs, and finally complexity analysis for both time and space taken by the appropriate code. So let's start with the first problem. The problem we are given with this letter combinations of a phone number. This is a well-known leet code problem where we are given with a string containing digits from 2 to 9, and our goal is to generate all possible letter combinations that these digits can represent. So each digit from 2 to 9 maps to a set of letters similar to old mobile keypads as shown in the image. The mapping follows as 2 maps to ABC, 3 maps to DEF, and 4 maps to GHI, 5 to JKL, and 6 to M&O, and the 7 to PQRS, and 8 maps to TUV, and finally 9 maps to WXYZ. The sample input and outputs of the problem are: if the input is 23, we need to generate the all possible letter combinations using the corresponding letters from the mapping. For example, 2 that is mapped by ABC, 3 is mapped by DEF. So when we combine these letters, the possible combinations are AD, AE, AF, BD, BF, BD, CD, CE, CF. Then, if the input is an empty string, it will return an empty array, means that there is no possible combinations of letters. So the output will be an empty array. As same, if the input is 2, the combinations will be a 3 single separate characters since only one digit was given. And the problem's constraints are: the length of the input string is between 0 and 4, since there are two sets PQRS and WXYZ has 4 characters, and each digit is between 2 and 9. Let's see it by clear visualizations. So as I said earlier, this is how the mapping will follow. For the example input string 23, the first digit in the input string, that is 2, will be considered, and the possible characters of the digit 2 is A, B, C, represented as a tree for easy understanding. Then we will have the next and the last digit from the input as 3, which has the possible characters D, E, F. So these three each mapped characters that are D, E, F will be mapped with each character in the character set digit 2. So that are A, B, C. So this will make 3 into 3 totally 9 combinations. Thus the output is AD, AE, AF, BD, BE, BF, CD, CE, CF. Now we have understand the problem statement and sample cases. Let's break down the approach and algorithm to solve this problem step by step. First, we have to check if the input string is empty, since there is a sample case for empty input string. If it is, we simply return an empty list since there are no possible letter combinations. Next step is to define a list S that stores the corresponding letter mappings for digits 2 to 9, just like a phone keypad. We initialize a list named results as with null string, which will be used to store the possible letter combinations as we build them step by step. And the next step is to iterate through each digit in the given input string. For each digit, we retrieve the corresponding letter string from our list S based on the digit's value. We then create an empty list for temporarily storing the new possible combinations formed from these iterations. Next step is to iterate through each existing combinations in the result list and append each letters from the current digits mapping to that combination. So again we can store these newly formed combinations in the temporary list. After processing all letters for the current digit, we update the result list with the temporary list so that it contains the latest combinations before moving to the next digit. Finally, once all digits are processed, the result list will contain all possible letter combinations. which will be returned as out. Let's look into the source code. We have defined a class called solution that contains the function named letter combinations, which takes the string digits as input. First, there is a need to check if the input string is empty, as I said earlier, so it will return an empty list. Next, we should define list S, which contains the set of characters mapped to 2 digits 2 to 9 on a phone keypad. Then I initialize the list result with empty string, at where we will be storing the all possible letter combinations of a given input string. Now, I have used a for loop here, that is for I in digits. So it will iterate over the each digit in the input string. For every digit, the corresponding character set will from the list S will be retrieved. The statement, that is D is equal to S of integer of I minus 2, that is the input digit string will be converted into integer, and since the index is in n starts from 0 but our digits start from 2, so we have to minus the I from the 2, so the appropriate character set from the list can be retrieved correctly. Then I have created a temporary list temp to store new combinations. So our next step is to iterate through each existing combination stored in result and append every letter from the current digits mapping to that combination. These new words are then stored in temporary list. So this can be done by the nested loop statements that are for j in result having an inner loop, for k in d, and then temp.append of j plus k to store the combination in the temporary list. After processing all letters for the current digit, the result list will be updated with the temporary list statement, that is result is equal to temp, so that it contains the latest combinations before moving to the next digit. Once the all digits are processed, finally we can return result which contains the all valid letter combinations. So these are the screenshots of the accepted test cases after executing the code successfully. The summary of the submission given by the lead code is follows as you can see that there is a 0 millisecond runtime taken by the code and 17.1 MB of memory with the all 25 test cases were accepted. Now let's quickly move on to the complexity analysis of our code. The time complexity of our solution is order of 4 power n because each digit maps up to 4 letters, leading to an exponential number of combinations. The space complexity is also order of 4 power n since our result list stores all possible combinations growing exponentially with n. Since n is at most 4, this approach remains efficient, but for larger inputs, the exponential growth becomes significant. Now let's move on to the problem 2, that is the sum tree validation. So Jazz is working with binary trees and wants to determine if a given tree is sum tree. Actually, a sum tree is a special type of binary tree where each node's value is a sum of its left and right subtree nodes. Our work is to come with a solution that determines whether the given binary tree is a sum tree or not. So the input format is that first line will be taken as an integer n, which is the number of nodes. Then the n space separated integers representing the level order traversal of binary tree. The output will follow as to print the level order traversal of a binary tree and then printing whether the given binary tree is a sum tree or not a sum tree. Then we have given with the constraints that are n ranges from the 1 to 15 and array of I, that is every element of the array which ranges from the 1 to 400, even though the tree is not empty as per the problem description. So there is a chance that it will be empty in some cases. Next, we will discuss the sample input and output with few visualizations. For case 1, having 7 elements in the tree as per the level order traversal, that is 44, 9, 13, 4, 5, 6 and 7. The binary tree will look like this. Here, the leaf nodes are 4, 5, 6, 7. the nodes which has no more children. As per the definition of sum tree, we have to check whether the sum of left subtree and right subtree equals to this current node's value. Left subtree sums will be calculated by adding the leaf node's value 4, 5. So it equals to 9. Again, if we add this left subtree, that are 4, 9, 5, we will get the answer as 18, which are in the left side of the root node now. As same, for the right subtree, the sums will be calculated as 6 plus 7, which are the leaf nodes, so it equals to 13. Then by adding the whole right subtree, 6, 7, 13, we will get the answer as 26, which are in the right side of the root node now. So if we add these two subtrees value, that are 18 and 26, we will get the answer as 44, which is equal to the root node's value. So the given tree will be considered as a sum tree. Let's see the same for the other two cases. For the case 2, the binary tree will be taken the same from the previous case. The only change is there is a one leaf node, that is 63 instead of 7 from the previous case. So the leaf nodes are 4, 5, 6 and 63. The sum of both subtree, that is 18 plus 82, which is 100. But here the new root nodes value is not equal to this sum of subtree. So that is, this is not a sum tree. For the case 3, we have 13 as root element and 6 and 7 as leaf nodes. As simple, the sum of both leaf nodes equals to the root nodes value 13. So that this will be a valid sum tree. Let's go through the algorithm first. We start by defining the binary tree node structure, which includes data and pointers to left and right children. Next, we have to construct the binary tree in level order by creating nodes for each input value and assigning child node accordingly. Once the tree is built, we have to check if it follows the sum tree property by recursively computing the sum of left and right subtrees and verifying if each node's value matches the sum of its children. To display the tree, a level order traversal is used, which utilizes a queue and print the values sequentially. Finally, in the main function, the input values will be read to construct the tree, and the level order traversal of the tree can be printed. More importantly, the sum tree's condition is determined here. For that, we will use a if-else loop. If it is satisfied the sum tree condition, binary tree is a sum tree will be printed as a final output. Otherwise, the program will print it as binary tree is not a sum tree. Let's look at our code implementation. Here, we use libraries stdio.h for standard input and output operations and stdlib.h for dynamic memory allocation and usage of pointers. Then we directly jump to the main function. On that main function, first it takes the number of nodes that the binary tree going to have. So it can be read by simply using scanf function. Then an array called ARR is dynamically allocated using malloc function to store the nodes of the binary tree, which can be data freed. Here, the for loop is used to input the each values and store the value in array ARR. A structure named node is created using type def, allowing us to use node as a common name instead of the structure node every time. This structure contains an integer data to store the node's value and two pointers left and right, which point to its left and right child nodes respectively. To initialize a new node, we use the structure-based create function with the node's values to be assigned. This function dynamically allocates memory for a node by using a malloc function. Then, this function assigns a value to the node, making both left and right child pointers to null, which will be allocated in future as per the need. And this function finally returns a newly created node n in the structure format. After that, now continuing with the main function, the next line statement will be node star root is equal to construct of array comma n, which calls the construct function with the parameters as array of nodes and the number of nodes. The constructor function will take these parameters and build the binary tree. Next, the construction function. First, it checks whether the array is empty. If it is, it returns null. This suits for some cases since we are given with the no binary tree is empty. Next, it allocates the memory for an array of node of pointers using malloc function. So, this line creates an array ns that stores the addresses of the tree nodes. So, each element in ns will later point to individual node. Then, each element will be created as a node using the for loop. To assign the left and right children in a complete binary tree, we follow the structured approach. That is, we iterate through each node using this for loop. Then, the left child of a node at index I is found at 2 into I plus 1, but only if this index is within bounds, meaning that it is less than n. Similarly, for the right child, the index is found at 2 into I plus 2, ensuring it does not exceed n minus 1. This logic maintains the structure for a complete binary tree. Then the root node will be considered as a first element. Our next work is to print the level order traversal. I have used the level order function here, which takes the root node as a parameter. It checks the null conditions first. Then it creates a queue S with a size of 100 nodes using malloc dynamic memory allocation. Then the two pointers front and rear initialized with 0 are used to keep track of the first and last elements in the queue. Front points to the next node to be processed, while the rear points to the next available position to insert a new node, as per the queue's first in first out principle. Firstly, the root node is added to the queue and rear is incremented, marking the start of traversal. Next line is that this while loop ensures that the traversal continues as long as there are nodes in the queue, denoted by the condition front lesser than rear. The node at the front of the queue is dequeued and the front is incremented to move to the next node, so that it can be printed as the first node in the level order traversal. If the current node has a left child, it is added to the queue so that it will be processed in subsequent iterations. Same, if the current node has right child, it is also added to the queue for future processing. The while loop continues until front equals to rear, meaning that all nodes in the tree have been visited. Once all nodes are printed, a new line is added to print next output line. After the traversal is complete, the dynamically allocated memory for the queue is freed for better memory utilization. Now going back to the main function, our next step is to print whether the binary tree is some tree or not after printing the level order traversal of the tree. For that, I have used the if-else condition loop with some tree function call. We will see the isSumTree function next. This is actually an integer function, returns -1 if the binary tree is not a sum tree. Otherwise, it will be considered as a sum tree. IsSumTree function logic follows as: if the node is null, means that an empty subtree, it will be considered as a valid sum tree with a sum of 0. This acts as base case for recursion. If the root node itself a leaf node, meaning that it has no left or right children, it is considered as a valid sum tree and its value is returned, or else you can return 0 too. Leaf nodes are automatically sum trees since there are no children to sum up. The function recursively called on the left and right subtrees to find the sum of its subtrees. The ls stores the sum of the left subtree and rs stores the sum of the right subtree. This line tells that if either the left or right subtree is not a sum tree, thus -1 can be returned from any of these recursive calls. The main snippet is that the function checks whether the addition of the left subtree and the right subtree equals to the root node's value. If it is, the tree will be a sum tree. Here, I return the sum of tree instead of 1 to make it better to verify the sum values. We can also return value as a 1 since it is an integer function. Otherwise, -1 will be returned indicating that the binary tree is not a sum tree. So, these are the sample test cases passed, and also execution will result in the runtime of 3 milliseconds as shown in the image. Finally, let's analyze the both time and space complexities. The overall complexity of the tree function is order of n for both time and space. The construction function runs in order of n for time and order of n for space, while isSumTree operates in order of n for time and order of h for space, with h being the tree height. Also, order of n in worst case and order of log n in best case. Then the level order traversal function also has the order of n time complexity and order of n space complexity. So, the final complexity remains order of n for both the time and space in worst case. Thus, we have clearly discussed these two problem solutions by covering algorithm, sample input and output, and its source code explanation, and finally its complexity analysis. So, thank you guys for watching. Have a good day.